Okay, so this is our second PPT on logic gates, right? We will be covering previous year gate questions on topic logic gates, right? Let's just see some basics of logic gates. So we have 4 basic logic gates. Basic logic gates are OR gate, like this, AND gate, like this, NOT gate, like this, right? These are our basic logic gates. So OR gate operation, if two inputs are A and B, so operation will be A plus B. For AND, it will be AB. For NOT, if the input is A, it will be A bar. That is not A. That means if input is 0, it will give output 1. If input is 1, it will give output as 0. Right? And two universal gates, that is NAND and NOR. So these two are universal gate. Why? These two are called as universal gate because from using NAND and NOR, we can implement any other basic gate, or there are two other gates, XOR and XNOR. XNOR. So the function of how we represent XOR is represented like this, and XNOR is represented like this. So output of XOR Y is, if inputs are A and B, it will be AB, A bar B, AB bar of, or if we write it in POS form, it will be A plus B, A bar plus B bar. Right, and similar way we can write this XNOR output will be equal to AB plus A bar B bar. So these are all type of gates, logic gates, which we have seen. Now moving on to the questions. This was very basic, which we will be needing in order to solve the questions, right? Question number 1. Question number 1 says that for the circuit shown below, the propagation delay of each NAND gate is 1 nanoseconds. The critical path delay in nanoseconds is what will be the value. So it's saying that this is the circuit, right? And they are saying that there are 2 NAND gates. So each NAND gate will take 1 nanosecond in order to give the output, right? You have to find out the total critical path delay, right? Total path delay in order to find out the total output Y. Let's just redraw this network first. So how we can redraw this? This is gate number 1, A, right? The output is given to input of B, right? And other one, this is another connection, this is the another input of B. So what will be the another input? So output of A. So this is your A and this is your B. One output of A is given to this, right? And this is your input B. Here, this is your output. Now it's saying that if I am giving input A and B at a time, the output of A, let me rewrite these name of the gates because input are also same. So gate X and gate Y. So what will be it? So this is taking how much time in order to give the output? This is taking 1 nanosecond. Similarly, after 1 nanosecond, if it will be the input to this and B we are giving at the same time. So B and A are starting from t is equals to 0. From t is equals to 0, any value. This is A, this is B. But after 1 nanosecond, this gate X, after 1 nanosecond, it is operated. Right, after, let me draw it with this. This is 1 nanosecond, this is 1 nanosecond, this is 2 nanosecond. Right. So, and this gate X is operated after the resultant output will be getting, suppose, after 1 nanosecond. After how much time it will get? So, B is operated from t is equals to 0 only, right? If we talk about Y, so it will start getting the output at this particular moment after 1 nanosecond, and it will also take 1 nanosecond in order to give the output. So it will take another 1 nanosecond. So total amount of time, critical path delay will be 2 nanoseconds. 2 nanoseconds, right? 1 nanosecond for this. Now input B is active all the time, right? It will take 1 nanosecond, and now after 1 nanosecond it will give the final result, that is Q, right? Moving on to the next question. It says that consider a Boolean gate D where the output Y is related to the input A and B as Y is equals to A plus B bar, where plus denotes the logical OR operation. The Boolean inputs 0 and 1 are also available separately. Using instances of only D gate and the input 0 and 1, you have to select the following option. There are options. So this is like multiple select. You can select multiple options at a time. Right. So it says that you have Y, some D gate Y in which output is given like this. And you have two more inputs, 0 and 1. Right. Only D gates. So you can use n number of D gates, and you have two type of input, either 0 or 1. So we have to see that if we can implement NAND, we can implement OR, NOR or AND. I'll give you a one-liner thing for this. For any gate, if you can implement NOT gate out of it, NOT gate out of that particular gate, you can implement any of the four from that particular output. Suppose if it is this function of A, B is given as A plus B bar, right? How we can implement NOT from this? I have both the inputs 0 and 1. Suppose I can say that it is 0 and it is B. So A will be 0 plus B, so it will be B bar. So this is what kind of gate? This is NOT gate. So if we can implement NOT gate, we can implement all the other gates. How we can implement all the other gates? Let's just see this gate. A, B bar we can implement from this, right? So we can implement B bar. So that will be A plus B bar bar. So that will be A plus B. So that is your OR gate. So it says that OR gate cannot be implemented. So this is wrong. We can of course implement OR gate from this. Okay, this statement is wrong. OR gate is implemented like this. Now let's just see other. So we have to make this NOR also. So how we can implement from this? We can implement OR from this A. We can easily implement our NOR gate. So this will be 0. A, B bar is giving us A plus B. So this will be your output for this type of function, and this is your NOR gate, right? If I am saying f of 0, comma, f of A, B bar, f of A, B bar is giving us A plus B, that is OR gate, and I have to convert NOR out of it. So as I have told you, if I can make any NOT gate, I can easily make this. So if I take NOT of this, it will give me NOR, right? So we can easily implement nor. Yeah, that statement is correct. Now, what other gate we have to implement? Now we have to implement OR gate also, AND gate also. How we can implement the AND gate? Right. So how we can implement the AND gate? We can also see that f of a b, if I take a bar, so because this will give me a bar plus b bar. So this is what? This is nothing but ab bar, right? Applying De Morgan's. So a bar plus b bar is ab bar. How we convert this? This to this. A bar plus b bar, take both bar. So one bar will be converted, will convert this into a dot b, and this is your another bar. Let me rewrite it. So making bar on bar is not going to convert it. Suppose if I am writing a bar bar, so it will be just a only. It will not going to convert the Boolean algebra Boolean expression, right? So I'm writing this expression a bar plus b bar and bar bar, right? So from first bar, if I apply De Morgan's law, so this or will convert into dot, and there will be bar 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 because of these two bars. So two bars will cancel out. It will be a dot b bar, right? So this is what kind of gate, and we are getting also NAND gate out of here. So NAND logic can be implemented. We are getting NAND gate. Finally, again, if I take NOT of this NAND gate, I can implement AND gate, last gate, right? As I have told you, if we can implement NOT out of any expression, we can implement all the gates, right? Finally, if f0 will be equal to 0 plus a dot b bar bar, that will be ab, and this is your AND gate. So last question says that AND logic cannot be implemented. So this is also wrong. So option A and C. Option A and C both are correct. Right. This is how you can solve this question. We have been given a Boolean expression in terms of A, B, right? They are asking us to find out whether we can implement any of the other above gates or not. Right, we can implement any gate if we can implement the NOT gate. We firstly implemented the NOT gate, and we can implement other gates easily by solving it out. Right, moving on to the next question. Next question says that the minimum number of two input NAND gate required to implement 2-input XOR gate. Very easy, very common, very common implementation which we always do when we are doing the theory part, right? So how we implement it can be easily implemented by using 4 gates. So this is your implementation. This is A and B, and this output Y is nothing but A XOR B. So by using 4 NAND gate and by using 4 NOR gates, we can implement a XNOR gate, right? And similarly for XNOR gate also, we need only 4 NAND gates, right? Moving on to the next question. Okay, next question says that you have to find out, now this is some lengthy question because multiple gates are given and they are asking you to find out the total output. Why? Right. So let's just start solving it. I am writing some of the outputs here only. Right. So this is what? This is AND gate. This will be doing the dot product. Sorry, not dot product. A dot B. I went into vectors very quickly. Okay. So this will be A dot B and this is C and D. So this will be B dot C. Now here what's happening? This is input C, A dot B dot C. And now here what is happening? There are two inputs B dot C and A dot B, and XOR is happening. So A dot B, XOR B dot C. And finally in output Y, ABC XOR AB XOR BC. So let's just write the expression here. ABC XOR AB XOR BC. Right. So this will be the final expression. Now we have to solve this into one of these because this is the simplest conversions. Right. Let's just start solving. So how we write out the XOR expression? So as I have told you, A XOR B, we can write it like this. This is how we expand the XOR. So let's just expand the first XOR. Then we'll expand the other one. So it will be ABC XOR dot AB plus ABC dot AB, and this whole XOR with BC. Let's just open this. This is a whole bar. We can implement De Morgan's again. So that will be A plus, so dot will be converted into plus because AND gate will be converted to OR add complements. Right, into AB plus ABC A bar plus B bar, and this whole XOR with BC. Right, now we have to multiply this AB with all of these three. So if we multiply AB with the first one, so AB dot A bar. Now this is what? AB dot A bar. This A bar dot A bar dot A is equals to 0 and A dot A is equals to A only. Right. So if we are multiplying to complement numbers like 1 or 0, multiply when we are taking AND of it or multiplying it, we will get 0 only. Right. So this will give you 0. Again, this is bar here. So AB into B bar. This will again be 0. So this and this will be 0, 0. Last one remaining will be AB C bar plus. Similarly here, A plus A bar 0. B into B bar 0. This is only remaining term from above expression, and this is XOR with BC. We'll again open the XOR. A, B, C bar complement A, B, C bar complement dot BC plus A, B, C bar dot BC complement. BC complement. Right, they just open it again because this is a whole bar. We cannot multiply anything or divide, or sorry, multiply anything or do any AND or operation by using this whole bar symbol. So we'll just open them into single terms. A bar plus B bar plus C bar bar. So that will convert into C only. We can write it later. Plus A, B, C bar, and similarly B bar plus C bar. Right. So if we multiply this with this, that will be B, C, A bar plus this B into B bar, that will gonna give you 0, and B into C will nothing but be B and C, because A dot A is A, right? Plus, now here if we multiply B into B bar, then gonna give me 0, and C bar into C bar will be C bar only, right? So now if we solve this expression, now here taking BC as common, so it will be A bar plus 1 plus ABC. Now something plus 1 will be equal to 1. If we add anything, if we take OR of any Boolean expression with 1, that will result into 1 only. How we can see this? So suppose A plus 1 is equals to, it will be 1. If A is 0, then 0 plus 1 is also 1, and if A is 1, so 1 or 1 is also 1, right? So this will be BC plus ABC bar. Right. Now what we can do here, from here we can take B as common. That will be C plus A C bar. This will be open like this, right? So C plus C bar will be equal to 1. So it will be B C plus A. So this is your final answer, right? Just check it. Right, moving on to the next question. Next question says that a universal logic gate can be implemented by any Boolean function by connecting sufficient number of these gates, right? Gates appropriately. 3 gates are shown. So there are gate number 1, 2 and 3. Which of the following statement is true? So they are asking you to find out whether gate number 1 is universal, 3 and 2, or none of the gate is universal gate. Universal gate is what kind of gate? Universal gate is that gate which universal gate is that gate from which we can implement all other gates. So as I have told you before, like 2 questions, if you can implement not, you can always implement all the other gates, right? From this expression, this is just our basic gate only. F1 is x plus y. This is OR gate, basic gate, and not a universal gate. F2 x dot y AND gate, again not a universal gate. This is also not a universal gate because AND and OR are our basic gates. F3 is similar as we have solved in previous question. Now from this I can easily make NOT gate. Suppose function xy is equals to, right, if I am writing x 0, so that will be just x bar, and we can implement a NOT gate. Now if we have implemented NOT gate, from the particular expression we can implement any other gate, right? So yes, gate 3 is a universal gate which we have already seen. We can implement all the other functions if we can implement NOT gate, right? Moving on to the next question. Okay, so they are saying that a figure is shown and gate number 1 and gate number 2 are hidden in this, and they are giving you the final expression. So final expression says that it is AB plus C bar D bar. So they are asking you to find out the which of the following are gate number 1 and gate number 2. So now just tell me, this is what kind of operation, the final operation. So these two are terminals and input terminal. So this will be one input, this will be another input, and the operation happening is or. This is addition. So this will be some or operation happening here, right? And now we have to find out for this. Now gate number 2. Gate number, this we can easily say that this is what? This is a NOR gate. So this is C plus D whole bar. So C plus D whole bar we can open again by similar way. So it will be C bar dot D bar, right? C bar dot D bar. Now this gate we have to find out the final output of this gate should be AB, right? So the final output of this should be AB. So A and B, if we find out, if we add them up, so this will be AB bar, but we have to take note of it. So instead of this, this will be NOR gate, right? NOR gate. So this will give me AB. So if I add A and B, because these outputs, this is A bar and this is B bar, and I want to find out AB from this, right? So we can easily implement the complement inputs of any NOR gate will give you AND gate, right? So this is complement input of any NOR gate. This will give you AND gate. So these gates are gate G1 and gate G2 will be NOR and OR. So that will be your correct answer. Right. Next question. Okay. So a 3-input majority gate is defined by a logic function sum MABC is equals to AB plus BC plus CA. Which of the following gates will be represented by this expression? So this is quite lengthy. Okay, let's just start solving it. Let's just firstly write this M A B C complement. So this is given like this. So M A B C complement is B C plus C A whole complement. So just do the complement. A plus B dot B plus C dot C plus A. This is how we can write it, right? Now, and they are saying M A B C bar. So how we can write it? So this will be AB plus BC bar plus C bar A. Now they are asking you to find out this whole expression, open it. So now what they mean is, we have calculated this. Now this will become A, this will become A, this will become B, and this will become C. This is C complement. It is hidden here. Sorry, C only, not complement given. So this is C. So what we have to do is multiply this two, because this is what is happening, multiply these two because BC is happening, and multiply these two because CA is happening here. So this is how we will be opening this expression, right? Let's just open this expression. That's this complete expression. I'm writing it MX. Okay, so that will be A plus B bar, B plus C bar, C plus A bar dot. What is B? This will be the B. AB plus BC bar plus CA bar plus this into C. So AB plus BC bar plus CA bar into C, and plus finally C into first one, C into A plus B C plus A whole bar. Right, this will be the complete expression, so it like lengthy. Some question of gate are like to waste your time, and yeah, you can expect these questions. Okay, so this is, let's just start solving it. Let's just solve this expression first, because this bigger term is common here and here, so we can take it common and then solve the smaller ones. So we will take this common. So let's just take this common, a plus b whole bar b plus c whole bar c plus a whole bar. I'm taking this common, so terms will be ab plus bc bar plus c a bar, and this term c plus, now solving this, so c multiplied by a, b and c. Now c multiplied by c bar, again I have told you, so that will be 0. Again c multiplied by c bar, this term will be 0. So only remaining term from this expression will be a, b and c. Now let's just start solving this. Now we have to solve this expression. If we solve this expression, solve this part first, right? Let's just write it. So this is AB plus BC bar plus C bar A plus C. Now this is equal to C bar A plus C is equals to C only. This is from absorption law. Absorption law. So this is equal to AB plus BC bar plus C. Similar way we can apply absorption law here also. So this is AB plus C. If we open it, it will be A plus B plus C. Let me write it here. So this is A plus B whole bar, B plus C whole bar, C plus A whole bar multiplied by A plus B plus C plus ABC. Quite a bigger expression again. Now we can apply De Morgan's again here. So this will be A bar plus, this will be A bar, B bar plus B bar, C bar plus C bar, A bar into A plus B plus C plus ABC. Now we have to multiply each term with each of these terms. So multiplying A with A bar, B bar will give you 0. Multiplying A with this will give you A, B bar plus C bar. Again multiplying A with this will give you 0. Now multiplying B with this will give you 0. Multiplying B with second term will again give you 0, because B into B bar will be 0. Now multiplying this with the third term will be B bar, B, C bar and A bar. Plus, lastly, multiplying C with this will give you A bar, B bar, C. And multiplying C with this will give you 0, because this is what? C into C bar, and multiplying this with this again will give you 0. So this is A, B, C, and this is the final expression of, if we rewrite it again, so this is A, B bar, C bar plus A bar, B, C bar plus A bar, B bar, C bar plus A, B, C. This is nothing but A's or B's or C. So this is 3 input XOR gate. So this is the final expression of XOR gate. These are the 4 midterms, which are the midterms of 3 input XOR gate. Clear? This was quite lengthy, but yes, we can always approach with a solution.